Start. Hello, welcome to the last part of Advanced Materials Chemistry course. This is related to the device with the materials, and I'm Anil Kumar Chauhan. I work in Technical Physics Division of BARC, and also I'm professor at Homi National Institute. So today we'll start fundamentals of semiconductor physics. If we see the syllabus of this part, it includes photovoltaic, which has solar energy and energy conversion, fundamentals of semiconductor physics and photovoltaic cells, generation recombination in semiconductors, PN junction, metal semiconductors and heterojunctions, photovoltaic device fabrication and characterization, current status of silicon-based solar cells, advancement in photovoltaic research and design of new generation solar cells. That includes hybrid, quantum dots, DSSC, and perovskite solar cells. We will have a detailed discussion on all these solar cells. Then there is another part, that is thermoelectric materials, which we will cover fundamentals of thermoelectricity, Seebeck, Peltier, and Thomson effects, thermoelectric effects and transport properties, basics of thermoelectric devices, heat conduction in bulk thermoelectric materials, heat conduction by phonons. This is like related to thermoelectric materials. And then the important part is device-worthy materials, important elemental and compound semiconductors, and amorphous silicon, single crystal growth techniques, float zone, Czechoslovsky hydrothermal growth of silicon, growth of gallium arsenide, production of silicon and gallium arsenide wafers, growth of quartz crystals, thin film deposition techniques, different deposition techniques we will see, thermal electron gun evaporation, DC and RF sputtering, epitaxial film deposition techniques, CVD, VP, LP and MB techniques, and some techniques for like 2D and 3D printing, general 2D and 3D printings. So basically, if you see, this course is actually designed mainly for device applications purpose. And if we see in most of the devices, I would say more than 90% of devices, semiconductors are used. So that is the reason why the semiconductor part I am taking first, the fundamental of semiconductors, and in general, what are different semiconductors and how their properties actually can be tuned, something like that. So these semiconductors are backbones of almost all the devices. Now, first let us see what are semiconductors. So generally, all the solid state materials, on the basis of their electrical conductivity, we can group them into three different classes, that is conductors, insulators, and semiconductors. So a substance that conducts electricity is called a conductor. And in a crude way, this is actually a simple definition. Which does not conduct electricity is obviously will be an insulator. So then where the semiconductor belongs? The materials for which conductivity lies between the metals, or you can say conductors, and insulators. That is called as the semiconductors. So the typical electrical conductivities, if we see, so if we see here on this plot, the conductivity is here. So those materials which are very good conductors, electrical conductors, conduction in this class and maybe next couple of classes, when I say conductivity, I mean electrical conductivity only, not thermal. When we will come into thermoelectric materials, maybe we will have some thermal conductivity portion also, but here it's mostly electrical conductivity. So if we see this side, they are very good conductors. Silver, copper, aluminium, platinum, this we know how they conduct electricity very well. And this side like glass and some oxide materials and diamond, sulfur, quartz. they are very good insulators. So conductivity, if we say in the range of the conductivity is 10 to the power 8 Siemens per centimeter to nearly to this 10 to the power 2, somewhere we can say, you can call them as a good conductor, good electrical conductor. And here in this range, we can call them as a insulator. So conductivity, when the conductivity of material lies in this range, they are generally called as the semiconductors. So what is actually, first thing is that what causes electrical conductivity? The conductivity is actually a result of movement of electrically charged particles. When we say electrically charged particles, it can be ions, but in solids, ions does not conduct. So in liquid, electrons does not move. Free electrons are not there. So it is the conductivity comes from the movement of electrically charged particles. In solid substance, so the movement of free electrons causes conductivity. In solid substance, there is the holes are also actually holes does not move. Basically, only electrons they move, but ions definitely does not move in solid substance. Similarly, in liquid, if you go, there are no free electron in liquid, so only ions move in the liquid. Now, since we are in the solid state, so we will move mainly, you can say, when the conductivity is concerned, as far as the conductivity is concerned, mainly it is the movement of free electrons. Now, when you have a free electron, how it will move? So, these free electron moves under the influence of an electric field. If you apply an electric field is generated when you apply a potential or you apply a voltage, and then the electric field is generated, and that electric field exerts a force on the charged particle. Suppose here it's electron, then this force causes, or you can say, force electron or charged particles to move. Now, the next question comes, can pure atom behaves as a good conductor? Suppose we know very well that copper is a very good conductor. So suppose I take a pure atom of copper, will it conduct? Now, or gold or whatever materials we saw in the first slide, those which were good conductors, can I take their atoms and will they conduct? No, they will not conduct because actually there are no free electrons. When you have a copper atom, all the electrons are bound. You need to have free electrons in order to have a conducting material, or you have conducting conductivity inside that material. So pure atoms cannot conduct. Or you can say, if I take even in amorphous material of copper, say highly you can say disordered amorphous copper, if somehow I can produce that, it will also not conduct. So there is something actually which cause you can say free electron and their movements in these materials. So now suppose we want to make a conductor. So if somehow we can remove electrons from these or force the electrons to come out from the atoms, then and they becomes free, and then apply some potential or make them move by any means, then the material can conduct. So now we can see there are two important parameters, which are availability of free electrons and their capability of movement. These two you can say factors are if these provide the conductivity inside any material. Now next question comes, if somehow you remove an electron somewhere, can an electron attain all possible energies? If it is a free electron, then obviously it can have all possible energies. But what happens when electron is subjected to a periodic potential? like inside a crystal, or where the atoms or ions are, you can say, arranged in a periodic fashion. What will happen in that case? Can this electron will remain free, or when I said that electron can have all possible energy, that means it is almost free. Whatever voltage you will apply or whatever field you will apply, accordingly it will experience a force. So but when it is inside a periodic potential, it is not the case. Actually, it can, in that case, it can attain only, you can say, certain energies. Other energies it cannot uh, attain. This is the actually very important property, which is very useful in case of semiconductor physics. When we study semiconductors, it is that property of an electron inside a lattice or inside a periodic potential, where its movement or its energy is basically fixed, its movement can be controlled. That is the reason why semiconductor materials are uh, mainly utilized in the devices, because here the movement of electron can be controlled. Now let us see semiconductor. What are different semiconductor materials? Semiconductor materials is usually at absolute 0 Kelvin. All their, you can say, cells are filled and they do not conduct. But as the temperature is increased, then there we will come a little later how the conductivity is. So first let us see what are different semiconductor materials. So if you come to this group, this particular group, 4A, carbon, silicon, germanium, tin, lead. So all these, you can say, atoms has 4 electrons in their outer orbit. They with covalent bonds, and these there is actually no free electrons at 0 Kelvin. This class, you can say, is semiconductors. So silicon and germanium are pure semiconductors, while there are some other classes, means when you can combine these group element and these group element in a certain ratio, or if you want to say, okay, aluminium, one phosphate, one phosphorus, that also becomes semiconductor. So this portion of the periodic table shows semiconductors. The common materials used in semiconductors are shown in the dark yellow. These are elemental, and these other elements are used as the semiconductor in the semiconductor industry. The silicon is most important material as far as the devices are concerned, because it is very cheap and it is available in abundance. So device grade silicon costs much less than any other semiconductor material. Silicon is it is actually made from the silica, and the silicates are in abundance, and it comprises of nearly 27.7% of the Earth's crust. So it is means very easily silicon can be produced in these industries. So silicon is one of the most studied element in periodic table, and silicon technology is by far the most advanced among all the semiconductor technologies. Now, one part is the elemental semiconductor, which is silicon and germanium. Then there are compound semiconductors. What are those? The compound semiconductors are also having these are also having similar properties of a semiconductor, as name suggests. but they are not a single element compounds. So as I earlier told, aluminium and phosphorus, gallium, arsenic, indium, antimony, or similarly like some 3B and 6 elements, that is zinc, selenide, cadmium, telluride. These kind of these are the compound semiconductors. So there can be binary compound semiconductors, which comprise of group 4 and group 6 elements. Uh, where is the group 4 and group 6? Number one is 4 also is possible, like silicon and carbon. They form silicon carbide, which is also a binary semiconductor compound. Then 3,5 compounds, which are aluminum phosphide. Similarly, these are like example of 3,5 elements. Then you have 2,6 elements, zinc oxide, and all these elements up to. Then you have 4,6 element also, like PBS, PBSE, PBT, and then these are binary compound, means where two elements are joined together and make to behave like a semiconductor. Ternary compounds are where actually there are three compounds. So if you see in binary compounds, like we had gallium arsenide. So if some portion, some fraction of gallium is replaced by aluminium, then the compound becomes aluminium gallium arsenide. And when this X shows the fraction, suppose I have 50% sites of gallium are replaced by aluminium, then I will say aluminium 0.5, gallium 0.5 arsenide. So these kind of compounds, these are ternary compounds. Similarly, we can have quaternary compound also, where to both the compounds, like indium arsenide, okay, indium phosphide, some part of phosphorus is replaced by arsenic, and some part of indium or some fraction of indium is replaced by gallium atom. So this compound will become gallium X, indium 1 minus X, arsenic 1 minus Y, or this Y is a fraction, and for P Y. So these are different kind of compounds which are used in the semiconductor devices. So this is the same which I should have written here. So many of the compound semiconductors have electrical and optical property that are different from those of silicons. So that's why we are using, I can say, many combinations, because for certain devices we need one property. For another device we need some other property to be controlled. So silicon is not useful everywhere, so we need some other device, means other semiconductor also. Now, as I already said that when electron moves inside a periodic potential, and then this periodic potential comes from the crystals. So crystal structures plays a very major role in the device properties. So first, let us see typical some of the typical structures where a material crystallizes. So some basic crystal structures, this you may already be knowing. The semiconductor materials are generally single crystals where atoms are arranged in a three-dimensional periodic fashion. It should be in all three dimensions. Even 2D material may not behave exactly as we expect or as it behaves in 3D. A periodic arrangement of crystals or atoms in a crystal is called crystal lattice. Ideally, the lattice is actually a collection of points in space. When you put an atom or you can say molecule or a basis, then that lattice plus basis, then it becomes a crystal structure. So in a crystal, atoms are at fixed positions in all three dimensions, if you will see. Now, when atom is at a particular position, suppose we have a lattice, an infinite, you can say, array of points, and every lattice point has an atom. If we go to absolute 0 Kelvin temperature, then all the you can say atoms will be at rest. There will not be like any energy. As the temperature started to start to increase, the atoms gain some thermal energy and they start to vibrate. And how they vibrate? They vibrate around the centered around this fixed lattice point. So the lattices are basically dots, invisible dots, you can say. And if we repeat this dot uh, in exactly same fashion, then it becomes you can say periodic lattice. So every lattice, in order to it to have it to qualify to be a lattice, it must have a translational periodicity. Means suppose there is a one point, I am having one point at a particular space, and then if I move towards right, uh, then after a definite distance or a fixed distance, I should get another identical point. Similarly, if I move in y direction, I will get another point which should be identical to the first point. If I forget from where I have come, then I cannot make any difference between the first point and the second point. So, in like mathematical terms, I can write a translational vector T, which is U1A1, U1A plus U2B plus U3C, where U1, U2, and U3 are integers, and A, B, and C are translation vectors. So you understood, I have a lattice. Now suppose, for example, I consider a square lattice. So where from a point, if I want to move to another point, I will have to move, suppose the lattice parameter is A. If I move in X direction by A distance, I will reach to another identical point. If I start in y direction and move a distance, I will get another identical point. So similarly is the three dimension. If I move by certain integer a and then any integer b, then another integer 3 c, then I will get exactly the same lattice points. This is the property of a ideal lattice. So if I apply a translation vector, and then there are and some certain symmetries like translational and rotational symmetries. Symmetry is also very important in this. Then there are only certain geometries possible where I can you can say divide entire space, or you can say I can fill entire space. So these different distinct you can say 14 lattice types uh, are called as Bravais lattice. So what are these Bravais lattice? These are 14 different, or you can say distinct and different lattice types. If I keep on repeating them, then I can fill the entire space. So they are cubic, then they are tetragonal, orthorhombic systems, rhombohedral, monoclinic, triclinic. Now in cubic also we can have a structure or you can say Bravais lattice. This is base centered cubic where one point is at the center and there are 8 points here. I can actually the entire geometry I can represent in this way. Similarly, if it is a face-centered cubic, then at 8 corners, if I put now there is one more important point we must always remember when I say this point. Actually, it is a point. Many students get confused by considering this an atom. This is not an atom. This is an point, and that is also consider it as an invisible point. So here we have only 8 points here at the corners and then 6 points at the different faces. Now, when an atoms comes on this, it is also quite possible that all these points can have atoms also. So then it becomes a crystal structure of that particular. Suppose you have a NaCl, sodium chloride material, sodium chloride crystal. Then it is not like that here I will have sodium and here I will have chlorine. At every these points, I will be having sodiums and chlorine will be automatically accordingly adjust its position. Or I can put chlorine also here and then sodium will be at some point. In sodium chloride case, that distance is equal, but in some other crystals, it can be different. So whenever someone asks you a question or you think in this way, so sodium chloride is, you can say, one entity, and that one entity has to be placed at every lattice point. There is a typical example of cesium chloride structure. What it contains cesium at all the corners and then chlorine at the center. So actually it is not a BCC structure. It is a simple cubic structure because, as I said, every point should be having cesium here, and here also it should be cesium if it is a BCC structure. But in cesium chloride structure, here we have chlorine. So it is a simple cubic structure with a basis point of cesium and chlorine, which is actually displaced by half and half from this point. So my unit cell, or okay, say this, then it will be a cubic structure, simple cubic structure, not a BCC. I see many students, they get confused about this. That is the reason why sodium chloride and cesium chloride structures are always taught. So for any given crystal, there is a unit cell. What is that unit cell? Unit cell is a representative of the entire lattice. There can be many unit cells. Unit cell is that you can say smallest volume, or that volume, not smallest. That volume, by repeating it, I can attain entire you can say crystal structure. So I can have in a single I can have the primitive unit cell also, where only one lattice point is there, and I can have some other type of unit cell where I can have more than one lattice points. By repeating the unit cell throughout the crystals, one can generate the entire lattice. And now, why actually we are again repeating it once we have already done this in detail? The cubic structure, see, we are going to study the semiconductors, semiconductor physics. So the main class of semiconductors, which is silicon or germanium, they are actually have relation to cubic structures. And this structure is structure plays a important role in their properties. So cubic structure is very important as far as the semiconductor physics is concerned. That's why we will revisit this very quickly, not in as detail as we did earlier. So there are 3 Bravais lattice in cubic structures. One is simple cubic, where suppose I consider a monoatomic crystal, that means where the basis is a single atom. Suppose any atom you consider, suppose atom A. So in solid state physics, normally we consider atom as pairs. When we are not going into mathematics in detail, in solid state physics, let us consider them as a spheres. So there are 8 atoms. Now we try to you can say, make them solid or freeze them, then they can if it is a single a simple cubic, then there will be like 8 atoms here at corners, and if you join the centers, then you can draw this kind of cube where each side will be A and the angle will be 90, 90, 90. Similarly, it is here also. So in body center cubic, you have 8 atoms at, you can say, 8 corners, and there is one atoms which is actually there in between those 8 atoms. So by looking at these two structures, you can just imagine which one should be a preferred structure in these two. In these two, it should be a preferred structure because here is same identical atom of the same size has been actually, you can say, placed in between these 8 atoms. So there will be, you can say, there will be strain. Here, if you see, there are actually less strain. Now, if you come to this structure, which is the most important structure as far as the semiconductors are concerned, that is the face-centered cubic, in which you have 8 atoms earlier as we have here, and then at every face you have atoms associated. Now, this FCC structure is also called as the closed spec structure. So suppose you have atoms, when they crystallize from liquid. In liquid, all the atoms are moving in a, you can say, random motion. And the gap is also, there is no predefined gap, but the minimum gap can be, which can be actually, means when both atoms comes together, they cannot go inside. Suppose I consider a sphere, one sphere cannot enter another sphere. So the distance will be this much. So in liquid also, other than thermal energy, which keeps them away, they try to remain as close as possible, but not in any particular structure. So ideally, when spheres, all the spheres, they were running here and there in the liquid, and then when they try to become solid, they should ideally be crystallizing in a closed spec structure, because that is the minimum energy structure. So this I have already said. In bodies centered cubic, this is the body centered cubic structure, and this is the face centered cubic structure. So in face centered cubic, that has one atom at each of the 6 cubic faces, and in addition to the 8 corners of atom. In this case, each atom has 12 nearest neighbors. How? If you see this, there, if you try to count with the atom, how many nearest neighbors it is having, you will find that there are actually 12 nearest neighbors, and it's a closed spec structure. How you will see it is a closed spec structure, though it looks like spheres. It looks like this. This is a FCC structure where there is a atoms. Let us consider atoms at each point, and then at each face we have different. So at like 1, 2, 3, 4, 5, 6, 7, 8 atoms, and then there are 6 at different faces. So when they crystallize, the spheres, they try to become as close as possible. So this is the, you can say, the first ideal layer of any material when it becomes solidified. Now, if you want to add another layer over this, or of another layer of spheres, now you can put where one atom here, one atom here, one atom here, one atom here. That is the minimum energy, you can say, situation. Suppose you put one, suppose now you are getting another atom. So where it should fit, it should actually fit here. That is the best possible situation. And that is the most stable condition. As far as the energy is also concerned, that will have the minimum energy. Now if I try to explain, a material want to crystallize in a simple cubic, then the atom has to come and sit just above it, then here, and then here. You can see it is not so convenient situation. What derives atoms to crystallize in those structures in that case? Because this is not the favored uh, situation where the atom should be sitting. It is the heat of fusion or heat of crystallization. When a liquid turns into solid, it releases certain amount of heat. That heat has to be removed from the interface. And once you want, if you can remove the heat entirely from the interface, then it will go to the minimum energy state. But if there is certain amount of heat is left, somehow the thermal conductivity of the material is not that good. In that case, this will try to crystallize in other structures. Otherwise, the most preferred structure should be the closed packed structure. So now you will have atoms here, atoms here, atoms here, atoms here, atoms here. Now, when you come to a third layer, so third layer, there will be two possibilities. Either the atom can sit here, or it can sit at the center. So if it is like structure becomes the first layer, second layer, and third layer are different, then it becomes an FCC. So it is an FCC. Now this one side I am telling it is a closed pack structure, but on the other side I am saying a FCC structure. So actually, if you try to look closely, the FCC structure, if you see it from this side diagonally, it is actually a layer by layer structure. So you have here the 6 atoms, these 6 atoms, any 6 atoms here, any 6 atoms, any 6 atoms here, these two 6 atoms, and then at the center one atom, and then above that this kind of structure. So now why we are studying this closed pack structure? Because the most important material, silicon or germanium, they crystallize in FCC structure. Before I say what, there is another structure which is diamond structure. In diamond structure, what we have, it contains, it is two FCC lattices which are interpenetrating each other by one FCC lattice and another FCC lattice. Imagine one FCC lattice where you have all atoms at corners and at the faces, and then you bring another FCC structure of the same material and insert it forcefully inside the first lattice, such that the corner of the second lattice is exactly 1 by 4, 1 by 4, 1 by 4 from the 1 by 4, 1 by 4, 1 by 4 distance from this point. So diamond lattice consists of two interpenetrating FCC lattices. The basis, obviously, when I'm saying it is FCC structure is when there are points, 8 corner points, and then there are points at the each face. So in diamond structure, when I have actually brought another lattice which is of the similar structure but displaced by 1 by 4, 1 by 4, 1 by 4, I can always say that these two atoms at 0, 0, 0 and 1 by 4, 1 by 4, 1 by 4, they made, you can say, one basis. And then exactly same, you can say, in the same direction, I can keep on adding at each point, then I will get this structure. So then I can call it as an FCC structure. So diamond structure is an FCC structure. So there are 8 atoms in the unit cell. Each atom bonds covalently to 4 other equally spaced atoms. And why diamond structure is important? Because carbon, silicon, germanium, tin, they crystallize in the diamond structure. So silicon, which is the most common materials used in all devices, or germanium, which is also very important material, they crystallize in this structure. So that is the reason why always in every textbook we have a diamond structure. Not because diamond is expensive, but because it is an important structure which need to be studied in order to know the properties of silicon. So if you can see here, so the structure is like this. So there are 8 corners, carbon or silicon at every corner, and then this in between you have at 1/4, 1/4, 1/4 distance. Okay. So this kind of cone, or you can say here, if you say, if I stop it, so this kind of if you see it very you can say carefully, what you see, there are actually 4 atoms, one atom, second, third, fourth, and there is another atom in between. Now this is a, you can say, to show you people, but when the atoms are coming together, there is no gap like this. So every atom will be close to each other. So in these 4 atoms, you can imagine it like 3 atoms at the bottom and 1 atom at the top, and you forcefully insert another atom between these two, like here. So imagine a situation where you have 1 sphere, 2 sphere, and 3 sphere, and so now there is a void here. So now the next atom, when the next atom will come, you will place, or next sphere will come, you will put that sphere over these 3 sphere in between. This is a simple, you can say, face-centered cubic. But if you want to make it a diamond structure kind of thing, you just between these, you can say, 4 spheres, whatever space is there, that called as the tetrahedral void, you bring another sphere and forcefully insert that sphere inside this. Then you will be able to realize or understand what diamond lattice is, diamond structure is. So now this structure is, it has come from the FCC. We have already seen that FCC is a closed pack structure. When we see it from the another side, it looks like the planes, one plane over the another plane. You just imagine that crystal structure, the closed pack structure. Now in every tetrahedral void of that structure, you insert forcefully another sphere of the same size, then it will become the diamond structure. So in like if I say in 2D, so you will have at 0, 0, 0, 0 all atoms, silicon atoms, and then in these 2 corners you will have silicon atoms from the bottom 1/4, 1/4, and then here these are the face-centered atoms. These will be at half the distance of your lattice parameter, and then if you move further above, after 1/4 lattice distance, you will have 2 different two same atoms of silicon at 3/4 and 3/4. So now you have at the bottom layer, you have 4 atoms. If I move up, if I move 1/4 distance, 1/4 in terms of the lattice parameter. Suppose lattice parameter is A, then I can say 1/4, A/4 distance. If I move A/4 distance above, I will reach 2 atoms. Then if I move further, then I will reach here at the center of faces. I will have these 4 atoms, and then if I move further up, then I will get these 2 at 3 by 4. Then if I move further 1 by 4, then I will automatically get these 5, 1, 2, 3, 4 at exactly A, and at the 1 at the center. This was the diamond structure. There is another important structure, which is zinc blende structure. What is the difference between zinc blende structure and diamond structure? First thing, why it is important? There are 2 important classes of semiconductor materials. One is the silicon class, or where silicon, germanium, and like carbon crystallized. Not carbon in general way, but diamond structure. But silicon and germanium, they crystallize in the diamond form. There is, because why? Because they are elemental. You can say semiconductor. Entire semiconductor is 1. So size of all the spheres will be same. Like here, the size of all the spheres are same. Now what happens when the size is different? There are important classes of semiconductors like gallium arsenide, very important semiconductor material, very useful. So where the size of gallium is different than the size of arsenic. So suppose you have uh, such kind of materials or such kind of elements where the size is uh, very different, then the same diamond structure becomes zinc blende structure. So zinc blende structure is actually nothing but here. So you have an FCC structure. Okay, you can consider 2 FCC structures now. One FCC structure of gallium, another FCC structure of arsenic, and in the same way like we were doing with the carbon or with the silicon, then you interpenetrate another structure to the first structure. Then whatever structure becomes, it becomes zinc blende structure. Why it is important? Mainly it is important because gallium arsenide, zinc sulfide crystallize into this material. Zinc sulfide is also an important semiconducting material, but mainly it is because of the gallium arsenide. So it has a face-centered cubic closed pack structure. Zinc side is at now as similarly. So you have a tetrahedral voids of zinc, and in between those two, between tetrahedral voids of zinc, you forcefully insert an arsenic. So it has equal number of zinc and sulfur ion distributed on a diamond lattice, so that each has 4 of the opposite kinds as nearest neighbors. This structure is an example of lattice with a basis of 2 type of atoms. In diamond structure, the lattice was having 1 type of atoms, that was silicon always. So what are important materials which crystallize in this? It's gallium arsenide, gallium antimonide, indium arsenide, silver iodide, etc. So this is a brief, you can say, comparison between these 2 structures. These 2 are technologically important structures because many common semiconductors have diamond or zinc blende structures. They share the same geometry. In both the structures, the atoms are tetrahedrally coordinated. That is, atoms has 4 nearest neighbors. In both structures, the basis consists of 2 atoms. In one, it is both the atoms are same in diamond structure. However, in zinc blende structure, both atoms are different. So now, once we have seen the structure. There is another thing is within the crystal lattice. We now imagine a crystal as infinite number of dot points, and at every dot you have placed 1 atom. So if you can say go inside that material, you can see several planes. You can have, actually ideally you can have infinite number of planes, है ना? Because see, why infinite? Because every 3 point, if you make every 3 points, you can make a plane out of them. So you can have infinite number of planes. They are equally spaced but parallel to each others. These are called as the lattice planes. In atomic space, if the atomic spacing is different for two planes, the crystal properties along with different planes may be different. Suppose you have, if you are seeing in a direction which is an x direction, then you will see different properties. But if you are seeing a direction which is actually perpendicular to both x, y, and both x and y direction, not perpendicular, at a certain angle for both x and y direction, but not z direction, then you will see the interplanar distance will be different. So the properties, many properties, not all properties, the properties will be different. So that is the reason why we study the planes also and try to identify different planes, and then you can have those arrangement of planes. Then you have another arrangement of planes. There is a different you can say distance between this set of planes and different set of planes. If you are trying to see a particular property which depends on the distance of planes, because if you just tilt, you do not have any idea which kind of structure it is. So if something is happening there, it doesn't know whether it is a simple cubic or it is something else. So that is the reason why knowledge of planes or understanding of planes is also very important. So the electrical and other device characteristics can be dependent on the crystal orientation. A convenient method of defining the various planes in a crystal is to use Miller indices. This I will go very quickly because you should be having just an idea what the planes are. So these are what are Miller indices? So where the planes are represented in the certain numbers. So these are obtained by how these are obtained. Suppose you have a crystal lattice where you have certain parameters A, B, C, alpha, beta, gamma at alpha, beta, gamma distances, and then just a set or a plane by you have created a plane by adding any arbitrarily 3 points. Then this plane will definitely cut x, y, z axes somewhere. So then you take an intercept and then take the reciprocal of this number, and then you reduce this number to the smallest three integers by containing the you can say by keeping the ratio same. And then if you just enclose in this parenthesis, then this will be the Miller indices. So just to give you a feeling how it is. So suppose this is a plane, any arbitrary plane I have made it. These are x, y, z, and the lattice parameter. Suppose it is a cubic structure, and the lattice parameter is A. So this plane is cutting at 2A, the y-axis, x-axis at 3A, and z-axis at A. So then if I take reciprocal, so it will become 1 by 3 because it is 3A. So A by 3 will become 1 by 3. Then this will become y is 1 by 2. So and then z because it is 1, so I can do 1. And then the smallest three integers. Now I don't want to keep these as a fraction, so I have to multiply it by something to make it to make all these numbers as the integer number. So I will multiply it by 6, so it will come through 2, it becomes 3, and it becomes 6. So this will be, the plane will be referred as 2, 3, 6 plane. Some of you may be thinking why actually these things are done in this way. First means why do I need to actually divide this by like a by 3? I can simply say 3a, 2a, and a. What is the problem in that? This is having a concept because the properties, the many properties, they are actually governed by the reciprocal space. The measurements like in XRD and all those things, they involve, you can say the mathematical interpretation involves the reciprocal space. So these planes in reciprocal space can very well, you can say, represent the real planes. That is the reason why we go for the mirror indices by dividing these, not rather than simple one. Because these are measured usually by X-ray diffraction pattern. That is when you try to analyze an XRD, obviously a reciprocal space comes into picture. Now let us see the valence bond. Each atom in a diamond lattice is surrounded by 4 nearest neighbors. Why 4 nearest neighbors? Because as I told you, it's a tetrahedral void. There was a tetrahedral void, and we have forcefully inserted an atom inside that tetrahedral void. So now the nearest atoms are, which are actually, you can say, in touch to each other, are at the that tetrahedral void. So these will have 4 nearest neighbors. So then if I try to say in it, so this is like that. So it is half, half 0, 0, 0, half 0, similarly in this way, and at 1 by 4, 1 by 4, 1 by 4, and this will be, this atom is actually there is not this much distance. It is just to get a good visualization. So if we see in 2 dimension, I can have like I have a silicon, and then there is the electron are shared here. So each atom has 4 electrons in outer orbit, and each atom shares these valence electrons with its 4 neighbors. So this sharing of electron is known as covalent bonding, and each electron pair constitute a covalent bond. Now, this suppose had it been in a simple cubic structure, not in diamond structure, what would have happened? How many nearest neighbors it may be having in that case? Will it be 4? No. So how it will share actually? See, you need to have, if you want to share with someone, they need to be on the same terms which you have. You have 4 electrons, others is also having 4. If your 4 neighbors are having certain properties which are exactly identical, then only you would like to share. No? So suppose I am having a simple cubic structure in which I will be having on 6 atoms. One is x direction, one is minus x direction, another is you can say y direction, minus y direction, z direction, minus z direction. So there will be an issue. There will not be actually equal sharing. So now when all the atoms have been already shared, a bonding has been made. So why there is a conduction? Ideally, silicon should not be conducting because it had 4 electrons. All the 4 electrons had been shared. This has been the bond has been formed. So why it should be having a conduction? There are no free electrons. So although if I go to absolute 0 Kelvin, there will not be any conduction. This is right. But as we start increasing the temperature, so at higher temperatures, the thermal vibrations, they breaks the covalent bonds and ionize some electrons from the bond, not all electrons. What will be the fraction? That will depend on the Maxwell-Boltzmann distribution. Maxwell-Boltzmann statistics. So at a particular temperature, certain number of electrons will definitely have that much energy which is necessary to break the bond. So when a bond is broken, so the electron is free. When an electron is free, so suppose this electron becomes free, then it can move because it's side in the it is free. So then this electron can cause a conduction. But in order to cause it a conduction, first thing is that can it have all energies? No, it cannot have all the energies if it is inside a lattice. So that we will see how the bands are formed little later. So for an isolated atoms, the electron can have discrete energy levels. For example, the energy levels for an isolated hydrogen atom can be given by this formula. This so suppose you have a hydrogen atom, this will have definite energies. If you put n is equal to 1, you will have one energy. If put n is equal to 2, you will have another energy. So you will have different energy levels. What will be minus 13.6. Then if you put n is equal to 1, you will have minus 3.4. And if you put n is equal to 2, you will have minus 1.5. And similarly, so the electron which is there in a hydrogen atom, it can have only this much energy. If you give, suppose there is an electron, and if you try to give it an energy which is not exactly same of these values, it will not accept. Suppose it is having a 13.6 eV ionization energy, and you try to give it suppose minus 3.4 eV. It is not like that it will take this 3.4 electron volt, and then the remaining will be the energy of the electron, remaining electron. It will either accept it or it will not accept it. So now what will happen when I try to bring two hydrogen atoms together? So these levels, which were very, you can say, unique, very discrete, minus 13.6. As far as means when these atoms are very far, there is not a problem. As soon as they try to come together, what will happen when their wave functions start to overlap? Then the problem starts because of the Pauli's exclusion principle. What Pauli's exclusion principle says, say that no two electrons can have the same energy states or same energy. Now both the electrons of the atoms, the outer, you can say the electrons of that hydrogen atom in this case, now when they become part of one system, they cannot have identical energy. So what will happen? Eventually, the energy level, which was sharp 13.6, it should split into two levels, so that it can accommodate both the electrons. So when they are brought closer, the doubly degenerate energy levels will split into two levels by the interaction between the atoms, or by when their wave function start to overlap. And it occurs due to Pauli's exclusion principle, which states that no more than two electrons in a given system can reside in the same energy state at the same time. So an extra energy state has to be created. These are the example of hydrogen, just to explain you. You have two systems, and when you try to bring both the systems together, when as when they are very far, absolutely there is no problem. They can stay in the same energy. You can measure the energy. You can find that okay, the energy is same for like in the case of hydrogen. The ionization energy is exactly 13.6. The first excited energy level is at minus 3.4. The second is here, minus 1.51, and third is here at minus 0.85. When they are very far, this is very important concept. When you try to bring them together, as soon as their wave functions start to overlap quantum mechanically, they cannot have both the, you can say, they cannot have a system which is having a solution with energy exactly identical. And this is also restricted by the Pauli exclusion principle. So eventually what will happen that that energy level, which was actually a sharp level, a distinct level, a discrete level at minus 13.6 or whatever level it will be, you can say, splitted into two levels, can be very close to each other, but there will be two distinctly different levels. This was the you can say the simplest case when you try to bring two hydrogen atoms. But hydrogen atoms we always study just as a test purpose because the simplest one. It is having just one proton, one electron, but that is not the real case. Now let us try to see if I have a hydrogen. If I try to bring hydrogen atom and hydrogen atoms together, then what should happen? And we try to bring them as close as possible to each other so that they are interacting with each other. Their wave functions are actually, you can say, influencing the wave function of other hydrogen atoms. All the, you can say, wave functions of every hydrogen atom should be influencing the wave function of other hydrogen atoms. In that case, wave function of the electrons in that hydrogen atom. So in that case, what should happen by this simple example? They should be actually splitting into n levels. If you have understood this, then things are easy. So if n isolated atoms are brought together to form a solid, now they are very important thing when they are in solid, when they are liquid. In the liquid, they are totally different. When they are solid, they are on a lattice. They are on a periodic lattice. There is a periodic potential. And that makes a lot of difference. So it is not if you bring them n atoms, isolated atoms together in the form of amorphous, they may not interact with each other. So the wave function will not be actually, you can say, in a most constructive way, they will not influence each other. Though they will, but it will not be the you can say the overall. If you average everything, it will not be the same. So if n isolated atoms are brought together to form a solid, the orbits of the outer electrons of different atoms overlap and interact with each other. So this interaction, including those forces of attraction and repulsions between atoms, causes a shift in the energy levels, as in the case of two interacting atoms in last slide we saw for the hydrogen atom. So, but now in this case, in place of two levels, we will have n separated but closely spaced levels. They will be formed. So, if you have like if I start from here, when the distance is very large, in that case, every atom is having a level which is very unique, or you can say very sharp. Ideal, if you consider an ideal case with absolutely narrow width, when you try to bring them together, so close that they started interacting with each other. In that case, these will start to split. Now at a distance A, what is A? A is a distance, a lattice parameter. Suppose I consider only cubic crystal. So now every atom is at a distance A, and their wave functions are also, you can say, interacting with each other. So at a distance A, then these levels will split into n levels. This is clear. This should be clear. When n is large, the result is almost continuous band of energy. Suppose n is very, very large. Suppose n was 2, then you had 2. If n is 10, you will have 10. If n is 100, you will have 100. If n is 10 to the power 23, you will have 10 to the power 23. And how large this number is? Very large. So you will have almost continuous band of energy in that case. So this band of n levels can extend over a few electron volts at the interatomic distance of a crystal. Interatomic distance means when of few angstrom, where normally the interatomic distance when they are very closely packed, that is decided with the size of your atom. What kind of atom you are using, how closely they are actually packed. If it is FCC structure, they go very close to each other. They almost touching to each other. So interatomic distance will be 2r, if r is the radius of one atom in that case. So at those levels, so this will be n. So now under this situation, when you have created a system where actually there was no discrete level but a band, then the electrons can no longer be treated as belonging to their parent atoms. And these electrons will be actually, they will belong to a crystal as a whole. Suppose, as I tried to say initially, that you had a copper atom. Now you have a copper atom. The copper atom cannot conduct because the electron, the copper electron belongs to that particular copper atom. But when it comes inside a crystal, and a crystal is perfect crystal, ideal crystal, where the copper atoms are exactly sitting at a definite distance to each other. In that case, the the energy levels for those outer electrons, they will form a band, and every electron of that entire system, of the entire, you can say that lattice or that crystal, can take any of those energy, but not same. There will be different. Though it is very, very, the difference is very, very large, but they are definitely different. So then, but they are continuous, almost continuous. So, but all those electrons now will not be treated as of a particular atom, but they will be treated as they are belonging to the entire crystal. That is the very important thing everybody must remember, or you keep in your mind, that inside a crystal, it is not that electrons are bound to a particular atom. I'm talking about the valence electron. Please keep this in mind. Do not consider that all the even the core atoms are also belonging to others. So I'm talking about because we are talking about the energy level, possible energy levels of uh, the electrons which are taking part in the conduction. That is the property which is used in the device applications. Now you will say why the core electron will not behave in the same way. They should also behave because they are also fermions. They should also follow Pauli principles. Yes, that is also right. But they are inside core. See, outer orbit is very, you can say, the bigger one. Inside, the distance is very, you can say, just imagine this way, the core electrons, the wave functions of the core electrons does not interact with each other in the same way as the wave function of outer orbit electrons are interacting. So if when they start interacting, they will also start doing something similar. But if the core electron are very very close, you can say, to the nucleus. You know from the basic science that there is a large difference between, you can say, outer orbit and the core, the inside orbits. So now let us come to silicon. Let us try to see this silicon. Why it is not? So silicon, it has these inner orbits. This one is having 2 electrons. This one is having, you can say, total there are 14 electrons. So out of these 14 electrons, 10 electrons are inside these 2 orbits. That is 2 here and 10 here. And inside the outermost orbit, you have 4 electrons. So these 4 electrons, these are valence electrons. Now these 4 electrons, we also, means all of us know it very well that because of the you can say hybridization, they form 3 sp3 hybridized orbitals. That was you can say in a simple basic science we studied that. So the 4 remaining valence electrons are relatively weakly bound. This we know, and involved in chemical reactions. So now these 4 electrons, it can have 2 are there in 3 s orbitals and 2 are there in 3 p orbitals. So however, see this 3s subsets, we know it has L is equal to 0. So this can have only 2 quantum states per atom. When n is equal to 3, L is equal to 0, it can have only 2. However, the 3p subcell, which is having L is equal to 1, it will have how many? It will have 6 quantum states. So now in this, you can say outer orbit, you have 4, you can say, electrons. But how many quantum states you have? You have 2 plus 6. So you have, actually you have 4 electrons, but you have 8 quantum states. Now, so one silicon atom is having 2 electrons in S state and 2 electrons in P state. However, 4 P state are still vacant because it can have more electrons there. And when they are actually in, you can say, single atomic state, they are so far to each other and they are not interacting with each other. In that case, what will happen? Suppose I consider n electrons now, as we did in the in the previous example. Now I have n silicon atoms, and so how many 3s state will be there, which are filled? You will have how many 3s state you will have? 2 into 3s. 2 into n, because there are n electrons, and then you will have how many 3p you will have? You will have 2n 3p also. And how many vacant state you will be having? You will have 6 vacant states. So you have 3s state, which is actually lower energy. You have 4s 3p, which is slightly higher energy, but you have 2n electrons because you are having n atoms. So definitely you will having 4n electrons in the you can say 4n valence electrons. Out of those 4n valence electrons, 2n electrons will be in 3s state and 2n electrons will be in 3p state. And how many 6n states will be actually vacant? Now this is when they are very far. Now lattice, this is let us see, this is a lattice spacing. Lattice spacing means they are, but they are very, very far. They are not interacting with each other. Now, when we try to bring them close to each other, this silicon, I slowly, very slowly, I try to move it towards this. So, when n isolated atoms are brought together, as the interatomic distance decreases, the 3p and 3s subsets of all the n silicon atoms will start interacting with each other and they overlap to form bands. See, in like when we studied a single, you can say, we considered a single level, and when we tried to bring all of them together, we saw that single atom has actually split it into n levels. When we try to bring n silicon atoms, where this is also certain, this is also some level, this is also some level, these are also some levels. So all these states are there. These are quantum mechanical states, so these states exist. When we try to bring them together, then they start interacting and they start and they start and then they overlap to form a band. So when they come like this, at this distance, if you will see, their interaction start and then the splitting takes place. Splitting of these levels, 3s levels is taking place here, and splitting of 3p level is taking place here. Now, up to this point, suppose just put a bar anywhere. So if my distance, if I have brought all the n silicon atoms at this distance. Suppose at the, so line just a line draw. Okay. Now suppose I have brought all these silicon atoms. It is an infinite lattice. There are n atoms which are sitting at a definite distance, which is actually this distance. This is a lattice parameter. So what I will see that still there is actually 3s levels and 3p levels. They are still existing. If I try to bring them further close, and if I come here at this point, then what I will see, actually I can see the bond, these levels are actually broadened. So now I can see still there are the 3p electrons, they are separated, and the 3s electrons, you can say the levels are still, there is a gap, they are separated. But when I come, you can say at this point, what I see that all the 3p and 3s orbitals have actually merged into each other. Now these have merged, but how many states it is having? Now it is having, the states will always be there. Here it will be actually 8 n state plus 2 n state. Here the 8n plus 2n. So they will be all like, 6n plus 2n. So there will be 8n states here. Now what electrons will occupy? They will occupy the lowest energy states here, somewhere here. So at this point, you will see in this material, if I can crystallize a silicon material with this lattice parameter, then you will see there will not be any band. It will be a continuous, it will behave like a metal. Why it will behave like a metal? Because you are having 6n electrons, you can say 6n electrons, and then you are having actually 12 double the energy levels. So all the above energy levels are empty, and they below this all the energy levels will, all the, you can say, levels will be occupied by the electrons available in the 4n. there how many electrons are there? There are 4 n electrons, and how many states are there? There are 8 n states. So all the 4 n electrons will be occupying the lower energy states, and all the higher energy states will remain empty, and there will not be any gap. So the electron which is here at this point, they can attain any energy, they can take little more energy, they can move. Now, if you try to reduce it further, and the distance becomes here, then you see the energy, the levels are further starts to split. So now you can have 4n levels which are here, and 4n states, sorry, 4n states which are having this energy, 4n states which are having this much energy. So now this is actually a lattice parameter on which silicon crystallize. So if I forget this entire thing, I can cut it. This is a hypothetical situation. This part is also hypothetical situation, because it is crystallizing in 5.43 angstrom. So what is left with me is actually these energy levels, these energy levels. So I am having now 4n state of these energy levels, and 4n states having a variation of energy, but this much energy. So if you can say if I remove this and just try to plot it in just 2-dimensional figure. So this corresponding to this, this becomes my these energy states. These are also becoming another energy states. So now I have 2 energy states. This you must have understood. There are 4n here, there are 4n here. How many electrons I am having? I am having 4n electrons. So all those 4n electrons will remain here, and this is called as the forbidden gap. There is no energy level exists here. So electron cannot have any energy which is having a range from this point to this point. So this is called as the gap. Now, if somehow I can raise an electron, then if I can give energy electron, then it can have this state also. These are also 4n states. So they are equal energy states in this also and in this also. So this is actually the basics of formation of bands, and which is actually you can say, see, when they come to when they come to each other, now they are at this distance. This is I consider as 1.43 5.43 angstrom, which is the interatomic distance between two silicon atoms. So at a temperature of absolute zero, electron occupies the lowest energy state, so that all states in the lower band, what is this? This is uh, occupy the lowest energy states. All in the lower band will be full, and all states in the upper band will remain empty. All these will be empty. The bottom of the conduction band is called as the EC, and the top of the valence band called as the EV. So this energy is called as EV, and this energy is called as EC. This upper one is called as the conduction band. Why it is called as the conduction band? Because see, if you can just throw an electron into this band, then there are all the possible energy levels are, you can say, available for this to have an energy. Now you apply a volt potential, then whatever energy a potential will give, it will be ready to accept it. But when an electron is here at you can say at the top of EC, top of you can say EV, suppose an electron is here at this point, at this point. Now if you apply a voltage, what energy it will, first thing is the what force it will, EV by d, the force it will experience. Because of this force, it will try to gain an energy from its gain in energy in its original energy or add an energy in its original energy, whatever energy is here, EC, this energy will lie somewhere here only. Now this energy is not allowed, so it will not accept it. Understood? This is also a very important concept. One was when we bring those atoms together, bands start to behave differently because of the Pauli's exclusion principle. Then when you have n atoms together in a crystalline form, then these split and the bands are formed, and these bands are actually backbone of the you can say these properties. So uh, physically, the band gap energy Eg is the energy required to break a bond in the semiconductor to free an electron to be in conduction band and leave a hole in the valence band. So you require this much energy in order to break the bond. This energy, it is 1.12 electron volt. 1.12 electron volt is you can say very large energy if you consider the thermal part. At room temperature, you have only 0.025 electron volt the thermal energy. Then you cannot have 1.12 electron volt. But there will be certain energies. How many time? Maybe 5 more minutes we can take, na? No problem. So if this is clear, then we go to another important concept, and that is the energy momentum diagram. This was a picture when we tried to move from this side to this side, and we consider only two atoms, like we are moving only two, you can say, atoms, but actually there are n atoms, and they are moving from all three directions. So there is another very important concept, that is the energy momentum diagram. From this, you just bear always in mind that all energies are not possible. Just remember this point, because there is a gap. These energies are not possible. Now, if you see, the energy is related to the momentum by p square by 2m0, where there is some m is suppose some energy. So when I say that E is fixed, certain E's are not allowed. What does it mean? That certain P's are also not allowed. The momentum, that means it cannot move with all the possible energies. That is the actually, but ideally it should be this, but it is not in the same case in a conventional way we are thinking. Why it is not? Because the electron, as soon as it gets an energy, it becomes a wave. It starts behaving like wave. More the energy, the wave, you can say, wave nature dominates over the particle nature. And so now you imagine some particle is moving which can have any energy, but can a wave have every energy? You have suppose you consider a string, you try to just you can say just press one from one side. Can all wave be constructive? Can it have all kind of wavelengths, all kind of frequencies? No. So when actually electron is a wave, then things are slightly different. Just keep this also in mind. So when you are thinking that certain energies are not allowed or certain momentums are not allowed, you just start thinking that we are talking about something which is wave, which is not an you can say particle. So the energy E of a free electron is p square by 2m. This we know, where p is the momentum, m is the free electron mass. Thus, a plot of E versus p will be a simple parabola. Why it will be parabola? Because p square. So if I put p here and E here, I will have absolutely this parabola. So in a semiconductor crystal, an electron in the conduction band is similar to a free electron, is being relatively free to move about a crystal. As I said, why it is free in a semiconductor? Because when it is in a conduction band, it can attain all the energy. So it doesn't matter to it whether it's a wave, it is a particle, whatever energy you will give, it will accept. So it's not a problem. However, when if you put everything in a periodic potential, either it is in a conduction band or it is a free electron is also plane wave. It can have any energy. When you put in a you can say in a periodic potential, because of this periodic potential of the nucleus, there are several constants. As we see in the earlier slide, when you put, there are certain energies which are not allowed. In a very crude way, I am telling. So if there are certain energies are not allowed, definitely those momentums will not be allowed. So then whether this will hold, whether this will hold, see, ideally it should hold. So if we do not consider that it will hold, then we will have some other problem. So what we actually start considering, that suppose there is a break here. Suppose, let us see, there is a break here. Suppose during this period it is not allowed. Then what we will say, that okay, this formula is correct. This is following. This is fine. But what has happened actually? My mass has become infinite. This is a way actually to you can say to tackle the problem mathematically, or to understand the problem, or to realize the problem in order to make a viable solution, or make a practical solution to the problem. So then a concept of effective mass comes. So in order to you can say in order to keep this parabola same, what we try to say, that the parabola is fine, but during certain you can say p values, the mass becomes infinite. So then for certain values mass become infinite, for certain values mass will become more, for certain values mass become much more. So the mass will be varying, but this formula will remain same. So the electron effective mass, that we call as electron effective mass, it depends on the properties of the semiconductor. Obviously, because it depends on the many properties of what material it is, how many electrons it is having, and what is the lattice spacing, and what is the you can say the other crystal structure. Not only lattice spacing, but the crystal structure in which it is forming. And then when you put all them together, how their levels will be interacting with each other, how they will be split. All those things will come into the picture. And so what if you then you will have you can say a curve, this PE curve. If you differentiate it with respect to P, but you will get, actually it should be the M, but now we will call it the effective mass, and inverse of this d by dp you will get the. So pictorially we can say we have now a conduction band, now we have a valence band. So in conduction band, if we try to say the effective mass, which is you can say 0.25 of m0, and in the valence band it will be equal to the m0. Now the narrower the parabola, corresponding to a larger second derivative, and the smaller the effective mass. So if this parabola is very narrow, then you can say the effective mass is smaller. So if effective mass is large, that means electrons are not moving. If effective mass is infinite, then electron cannot move at all. If effective mass is very, very less, then it can move. So this is maybe we will close after this slide. And then the remaining we can do in the next class. So in a very, you can say whatever I have said, just to summarize this particular thing. So what a crystal is you have positive ions, many positive ions. They are actually placed at fixed distance a periodic distance. So you see the distance between these two are same, the distance between these two are same. When you are at this you can say ion or at this ion, you will not make out any difference. We will see the same surroundings. Yeah. Now, if an electron moves from, you can say, from this point to this point, what it is seeing? It is seeing these ions, these ions, these ions. See, this ion is positive, electron is negative, it will get an attractive, it will get an attraction, it will get attraction from this also, it will get from this also, all these things. So if I try to, you can say, plot this potential, so this potential ideally actually it should be like this. So when it comes here, it will be, the potential will be here. When it is somewhere here at this distance, when it is actually very close to ion, the potential will be very you can say less negative, and then when it is far, it will be different. So when it moves anywhere, it will definitely see a periodic potential. So this is a periodic potential. So when I try to, now this is actually, electron is not a particle, but it is a wave. So when a wave is moving inside this periodic potential, or consider particles, then we consider Schrodinger equation. We solve the Schrodinger equation for this, and the solution of this particular problem comes like this. This is left hand side and this is right hand side. This is a long mathematics. I have just skipped all that mathematics. It is not necessary. You just need to understand why the bands are coming. So if you see, the solution of the Schrodinger equation are like this. So when the solution will exist, you see on the right hand side there is terms cos A, Ka. We know always from our basics mathematics that the value of cos cannot become more than 1 or less than -1. So this value has to be always between +1 and -1. However, if you try to plot this is also an oscillatory function. This is sine, this is cos. If you look and say add all these terms, this is the actual curve which you will be getting. So this is left hand curve, this which you will be getting. This is right hand curve, which is actually, it has to be between 1 and 2. So in order to have a possible solution for this problem, you need to have the values between +1 and -1. Otherwise, for all other values, there will not be any solution. So these values for which there is no solution, these are the forbidden values, and these comes as the band gap. This is the mathematics behind the band gap. So we saw how when we bring together in a qualitative way, we saw the bands are formed. We saw we try to see mathematically also, though we didn't try to solve the problems, but you can go to any physics book or any solid state book. This is a standard chronic penny model where this solution comes, and this solution there exist only solutions where this cos Ka, which is right hand side, falls between +1 and -1. So solution will exist only for this region, for this region, because here this value is between +1 and -1, and this value is also between these two. So both the values should be +1, and it will exist between +1 and -1. So just two more minutes. I'll finish. Something is coming.
Yeah.
Okay. So okay. So with this, now if we try to plot this in a same way, okay, say EK curve, so you will find there are certain gaps here, which I was telling you earlier. So these gaps are corresponding to where there is no solution exists, and these are Brilliant zone. For the time being we can forget, because it's much beyond the you can say of the present syllabus. So this way we can understand the formation of the bands, and these are like okay, this maybe we can cover too. So I think we should stop here, and there are some some part is left in this lecture. We will try to cover that in the next lecture. So there is one more announcement. The next lecture of 31st will start at 4:30, and it will be 1.5 hours. So it will be from 4:30 to 6 o'clock. So now you please keep it in mind. I have certain some other assignments, so I will be. So next lecture will be at 4:30. So please keep it in mind. And if you have any question, you can ask me. I'm ready to answer. On 31st August to 6. On 31st. Starting? नहीं एक ही lecture होगा. Other all lectures will be. Next lecture will be starting at 4:30 p.m. to 6 p.m. Yes. On. Okay, last minute. On 31st August 2023. And if required, you can send in email also to participate because I have some other important. So any question, I'm ready to answer if someone is having question. Well, if there are no question, then bye. See you in the next lecture.